afternoon, guys. It is a Tuesday afternoon. That can only mean physical sciences here on Tenfold Live. I am Tobile Nkosi, and thank you so much for tuning in today's show. Today, we are again doing physical sciences. We're revising on paper number 1. I want to send tons and tons of love to Liberty. Thank you so much for sponsoring the show. Thank you once again for giving us the opportunity to actually support and actually help the class of 2021 with their finals exam papers. The prelims, the prelims actually start next week Monday, which is the 23rd, so all the best for that. Grade 12s, if you haven't done it yet, please do download the Tenfold education app. Now is the time to download that app. Your prelims are starting soon and you need all the question papers and all the practice that you can get. Remember, physics is all about practice, practice, practice. You can see where your loopholes are. If you're wondering what question paper we're doing today and you'd like to join in some fun, please do send a hi to the WhatsApp number on the screen and you'll meet our friend Dex. And just like you, he wants to learn. If you're looking for another platform where we're active and where we can actually help you, and that is on YouTube. And on YouTube, you can join us and follow us on Mindset Learn. So without wasting any more time, today we're doing electric circuits, one of my favorite topics actually. So the foundation for electric circuits does start in grade 10, but it actually improves a little bit more in grade 11. In grade 11, that is where we find out how potential difference and how current actually then starts affecting resistors in series and parallel a little bit more than what we did in grade 10. So what I want you to keep note of with what we're going to do is, if you can know that resistors in series have the same current, and different potential difference, and resistors in parallel, the current will split, but the potential difference will be the same. Remember, resistors in parallel are current dividers, where resistors in series are potential different dividers. So with each and every question that we're going to be solving, that is my first secret to actually solving any electric circuit. So the first one that we're going to do, it says the light bulbs are connected in a circuit with a battery having an EMF, so they have of 12, so they've given us that, volts, and an internal resistance. Remember, internal resistance is represented by that small r of 2 ohms. We must refer to the diagram below. Assume that the resistance of each light bulb is the same as that calculated in question 8.1.2 and switch S is closed. So another thing I just want to stress on, guys, remember, if we have an open switch as well as when we have a closed switch, the circuit actually does differ. Remember, if the switch is open, then electrons don't really jump to the other side. And when the switch is closed, then there's a flow of current. So you must be very careful. If the question paper says switch S is still open, then you know that it's a completely different ball game. If switch S is closed, then we know that there is sufficient current that is actually then flowing through the whole circuit. So now let's look at the circuit actually. So I can see that I've got 3 light bulbs, A, B, and C. I can see that B and C are parallel to each other, which means if you use your finger, you go all the way, the current from here will split between B and C, but the same current will flow through A. I can see that there's my switch, then I've got my EMF as well as my internal resistance. So the first definition, we must define the term power. Remember, every time you define, it's not an explanation. You're not telling the examiner what you think power is or whatever. It's a definition. It means that the words need to be precise and the examiner is looking for certain words in the phrase. So you cannot put some of the words and take some of them out. Try to remember it exactly as it is. What I always tell my kids, you cannot fail because you're lazy to read. So the definition for power is, it is the rate. It's not very different to the power we use, the definition for power in work, energy, and power. So it is the rate at which energy is converted and this is to other forms. To other forms in a circuit. And that is it. That is 2 marks for you. So it is the rate at which energy is converted to other forms in a circuit, and that is what power is. So number 8.1.2 says we must calculate the resistance of each bulb when used as rated. So now we know that they are identical, which means whatever total that we get, we're going to have to divide by 3 because they did say the bulbs are identical. So now let's see where we have most of our information. Well, something to take note of is remember that 2 are in parallel with each other, and then the other one is in series. I do have my EMF, which I am given. So I could actually use I could actually use a different formula to find out how I can actually find the resistance of each. So in the previous question, where it says in 8.1.2, we were therefore given the power. I just think the question got a little bit cut off in this one, but the power that we were given was 6. So they said that the power in the circuit is 6. So if we say power is equal to, I'm going to use the formula V over R, and my V is squared. Now everything else I do have. The power is given to me as 6. I am told that my EMF, or my potential difference for this battery, is 12. So I'm going to use it exactly as it is because the resistors are in the same circuit. So that will be 12 squared, and I am looking for the resistance. So I only tried this with one method because we don't have a lot of information. So for now, I cannot use the EMF equation because I don't even have the current that's flowing in the circuit. So you can't have an unknown of power, of current, of internal resistance, and this and that. Remember, in physics and mathematics, you need to only have one unknown, and then you're more likely to actually solve the problem. So with this one, I know that they are in the same circuit, meaning the same power with the whole circuit. So that's why I'm then looking for R. So let's find the value of R. So 12 squared, this one I can do in my head. That will give me 144. So remember, let me just do it the long way so everyone gets what I'm doing. I'm going to cross multiply. 12 multiplied by 1 squared will be 144, and 6 multiplied by R will be 6R. Now I need to find the value of 1R. I'm going to have to divide both sides with what's bothering my R, which is the 6. I'm just going to work over there. So this and this will cancel. So let us find the value of 1R, or 1 resistance. 144, and that is all over 6. Oh, let me just do that again. So I've got 144 over 6. There we are. So it means that each resistor has got a resistance of 24. Remember your SI unit, which is that funny looking sign which we call ohms. So that is a resistance, or the value of each resistor, because they did say they are identical. 8.1.3 says we must calculate the total current in the circuit. Now you must remember, in order for me to calculate the total current in the circuit, I must first find the total resistance in the circuit. I am given my EMF of my circuit. I'm also given the power of my circuit. So therefore, I can calculate the whole current that's actually flowing through. So let's see how we're going to do this one. Let's just go back to the circuit, and then I can see what we're going to do here. So let me see what I do have. So I do know that I do have an EMF, I do have an internal resistance, so this means I can already move to the formula E is equal to I R plus internal resistance. I do have that. I am looking for my current. I can find my total resistance because these two are in parallel. This one is in series, and my internal resistance, that is also a check. I do have that, so it means I can use this one. If you are struggling with electric circuits, or you're struggling with which formula you can use, how I always go about it is find a formula and then see what I actually have and what I can actually get in order to plug in with that formula. So with this one, I've only tried it in one way, not in another way. I didn't use the power one, but I'm going to show you in which way, in this way, how you can actually solve it. So I've got EMF, I'm looking for current, I can find my R total, and internal resistance was given to me as 2 ohms. So let's do it one step at a time. And I can see that it counts 5 marks, so it should be quite a lengthy step. So remember, I must first find my internal resistance. I'm going to start with the parallel ones. So I'm going to say 1 over R parallel is equal to. So you want to show the examiner with the formula that you're going to be working with 2 resistors which are in parallel. If you do choose, you can call it RA or RC and RB to show the examiner which 2 you're working off, or you can give the value of them being 24. I'm just going to work with it like that. Also remember the 2 lines to show that it is in parallel. So now I can say 1 over 24. They did say the resistors are the same. So in the previous question, we found that each resistor has a value of 24. I'm going to put that in my calculator exactly as it is. So that will be 1 over 24. Plus 1 over 24. So I'm going to do it in 2 ways, just so that everyone knows what I'm doing. This is 1 over 12. But now remember, if you are calculating resistors in parallel, we have to do what we call the tip and tap, or what we call the reciprocal. This means that the denominator becomes the numerator, and the numerator becomes the denominator. The trick of the matter is, with resistors in parallel, the total resistance must be smaller than the smallest resistor. This means in this case, my smallest resistor is 24 because they're all alike. It means that the total resistance for those resistors in parallel, being B and C, should be smaller than that, meaning that my answer should be smaller than 24. If your answer is greater than 24, then there's something that you did wrong. So in this case, now I'm going to do the tip and tap. This one comes to the top, this one comes to the bottom. That becomes 12 over 1, which means that my total resistance for resistors in parallel is then 12. I just want to extend this. I know that some teachers use this method where they say 24 plus 1 over 24, and then they use the inverse of minus 1. I'm going to do it that method as well, just so that nobody feels left out. It is a quicker method. It is an easier method. You can also just use the first method that I showed you. Use this one just to double check if you do have that correct. And you see, as you can see, we get 12 once again. So this also means that I have 12 ohms on this side. Just want to go back up, which means that these two resistors here collectively give me 12 ohms. Now remember, with resistors in parallel, once we find the total of these resistors, they become one resistor. So hypothetically speaking, if I was to close out C and then C and B are now represented by this one, not adding them, but becoming one light bulb. So this whole part here doesn't exist. Just want to make everyone see. So this is not there. Have an imagination. Can you now see that A, collectively with this light bulb here, are now in series? So A and B are now in series because B and C, we found the total. The sum of them gives us 1, meaning that they now become one resistor. Just take that away. Just wanted to make sure everyone saw that. Now I'm going to find the total resistance for the whole circuit. That was only for the resistors in parallel. So I can just want to take this off as well. So we're not done. So now I'm going to say R. You can say R total or you can say R external. So now remember, I first found the resistors in series plus the total of the resistors in parallel. The resistor in series, this one was the A. Since it was right there moving by itself, as you can see, the current was flowing before it split between B and C. And remember, they said they are identical, which means that A will also be 24 ohms plus. We found that the total resistance for the resistors in parallel gave us 12 ohms. So I'm just going to add that by 12. Let's see if I can do this in my head. So 2 plus 1 gives me 6, and that gives me 6. So the external resistance will give me 36. Still not done. The question said we must find the current of the circuit. I am given internal resistance as well as an EMF, so I can therefore go right straight to this formula, which is equal to E is equal to I, R plus small r. Now guys, you must always remember there is more than one way to getting to the correct answer, as long as you get to the correct answer and you show the examiner the steps that you're working. So some of us actually work all the way down. I am working side to side. Just make sure that you show the examiner what you work. Don't work on a piece of paper and then just plug everything in. You do get a mark for each and every step that you're showing so that the examiner can see the flow, that you knew that they were in parallel, this one was in series, and then how you're coming to the final current. The EMF of the battery was given to me as 12. They did ask me to find the current of the circuit. I did find my total resistance as 36. My internal resistance is that small r there on the circuit, was given to me as 2. I'm going to 12 on this side. I bracket 36 plus 2 will give me 38. This is now just mathematics. I multiplied n will give me 38i. Now I need to find the value of I. I have to divide both sides with what's bothering the I. In this case, it will be 38. This and this will cancel. Let's plug this one in our calculator and see what we get. So I'm going to have 12 divided by 38. And therefore, I get 0.32. Remember, if the third number is 5 or greater, it changes the 1 in front of it to a next number. In this case, we've got 5, which means it'll change the 1 to a 2. And that's how I get my current as 0.32. Remember, the SI unit for current is a capital letter A for amperes. Small letter a is acceleration, so let's not make that mistake. So that is then how. So I think the important thing was using this formula over here, was that my resistance was outstanding. I knew that some were in parallel, in series. I first found that, moved over to this side, and that is then how I found the total of I. So that wasn't too bad. 8.1.4. Now they're asking me to calculate the potential difference across light bulb number C. So let's go back to light bulb number C and let's see what is going on here. So the one thing I see is that A, since it's all by itself, it will have its own potential difference. I see that B and C are in parallel. I know that with the resistors in parallel, the potential difference will then be the same. So then it's one of two ways. I know that if I look at A, the sum of B and C will then give me the potential difference. So therefore, I can then use ratios. But then I still don't know what is going on. Remember, I've only found the entire current in the circuit, which means the current that will flow through A will be the 0.32. I do know that B and C are identical, which means it will have the same amount of current. So that's the first thing I should find. I do know that the resistance of C is 24. I did calculate that. Now, if I can find the current that is passing through C by using the ratio, since it will be a split of A in between B and C, I can therefore find the potential difference by using the formula R is equal to V over I. So I don't know if you understand my thinking here. But if I can find the current that will split between B and C, remember, I'm going to use R is equal to V over I. They are looking for my potential difference. I don't have my current. I do know what current will pass through A. That's the 0.32. I do know that half the current will split down here. The other half will split down here. So therefore, I can find R. Now, it sounds all hunky-dory if it's a story, but you need to show the examiner exactly what you're doing. So there's various ways in which you could have done it. What I just did, I said I total will be, let me just do it the long way around. I'll say I total. So it will be the current that will pass at A, which would be the sum of the current at B plus the current at C. And how do I know this? Because A is in series, meaning that the total current in the circuit will pass through A. But B and C are in parallel and it will split equally because the two resistors are the same. So which means that the total current that will flow at A will be 0.32. These two are exactly the same, so I'm just going to say 2IBC because it will split equally. If you divide both of these sides by 2, so I want to see the actual split. Remember, it is for 3 marks, so you do want to show your examiner where you actually kind of got this understanding from. You could have used any forms of mathematics to explain it, but don't write it in words so the examiner needs to read. So here we get 0.16. So the current that will split at B and C will be 0, let me just double check. Was it 0.16? Yes, we've got 0.16. Remember, to 2 decimal places. The SI unit for I is therefore a capital I. I'm not finished. They did say they want the potential difference. What I have only figured out is the current. Therefore, I'm going to use R is equal to V over I. I'm going to make V the subject of the formula, which gives me V is equal to Ri. The resistance, it is number C, and remember C has got an identical resistance with A and B, which all 3 of them have 24. The current that we just calculated, the ratio of the current that will pass between C is therefore 0.16. Let's put that in our calculator and see what we get. Multiply that by 24. So my V will give me 3.79. I get 3.79. Let me just 3.84. I mean to say 3.84, and the SI unit for V is therefore then a capital letter V. So that's then how I would have done that one. Let me just extend my page here a little bit. So the next question says, explain why light bulb C in the circle will not burn at its maximum brightness. Let's go back to the circuit. Let's see what's happening in the circuit. Now remember, there's a big thing with resistors in series and resistors in parallel and so forth. So now if you look at resistor number B, it is in parallel to B and C. Remember, if you look at the formula, P is equal to V squared over R. If there is an increase in power, there's a decrease in resistance. Now, remember, if ever you have to be given questions like this, where they're asking you, why will it not go bright? Why would it be dim? Or what happens to the resistance or the reading on the ammeter and all that, those things, the examiner wants to see whether you understand the relationship between two compartments. For example, with this one, I can see that power is directly proportional to the potential difference, but it's therefore inversely proportional to the resistance, which means when my power goes up, my resistance then goes down. So now the question he is asking was, why is then C not shining at its maximum brightness? So in this case, I'm going to stick with this formula. P is equal to V squared over R, since power was one of my given sources. So remember, I'm going to say it out in mathematical terms as well. P is directly proportional to V, so which is power. Power is directly proportional to the V squared. And then let me just add on since the potential difference across light bulb C is less than the less than the operating. I've got the word operating. Then the operating voltage. The power output will be less. Just want to elaborate on this one further. Remember, we were told that it has 12 volts. The resistance of C is 24. The power of the circuit was then 6 watt. So now power is directly proportional to V squared. Since the potential difference across the light bulb C is less than the operating voltage, the output will then be less. So that's why then it will shine a little bit brighter. So anything along those lines where you're showing the examiner that you know that there's a relationship between these two, you could have said in any form. It's also always nice to show the examiner that you know that there's directly proportional, that there's inversely proportional, that you do know why it will then be dim or why it would then be a little bit more brighter. So this question actually continues all the way this side. Here's the part that was cut off on the previous one. So here we've got 8.2. So by 8.2, we're told resistor A, B, C, and D are connected to a battery having an EMF and negligible internal resistance as shown in the diagram below. So I've got A and C are in parallel together as well as in parallel with the sum of B and D. This means that B and D are in series together, however, will be in parallel if I looked at each line collectively. So I've numbered it 1 to 3. Then they will be in parallel with each other. So number 8.2.1 says, give a reason why the current in A is greater than that in the current in C. You can see that A will be in series with this one and this one, but I can also see that the current in A is the total current in the circuit before it splits between 2 and 3. That is for 2 marks. So the examiner wants to see that you can see that some of the resistors are in parallel with each other, but one is therefore then in series. So we can therefore say for 2 marks, for number A, since the total current will pass there, that the total current, Tobile cannot multitask, the total current passes through A, and for the parallel parts and for the parallel portion, there are branches, or the branches therefore there are branches, therefore only a portion then, portion of the current will flow through. But I think what the examiner is looking for here, okay, let me just write this before I make a spelling mistake. So I think what the examiner is looking for here is for you just to say that the total current will be at A, but then it will split between these ones. And that was only for 2 marks. Now we have another theory. So now they are telling us that resistor number C is now removed. How will the current reading in B compare to the current in A? So we remove C, how will B and C compare? Let's go back up here. So we remove C, so all of that goes away. So if we remove C, I don't know if you can see it, but let me use a different color. So I want to show you that this actually then changes to a series circuit. So this moves all the way around, there's no branches, it goes all the way up, and so forth. So if we remove resistor number C, this actually becomes a series circuit. So then we can say that the circuit or the current in A, I can say that let me start like this. The circuit becomes a series circuit. Which means the current in B will be equal to the current in A. And that's that. Let's see. I think that was our last question. But this was actually a very nice question. But here the examiner was just technically looking at whether you can visualize that if something is removed or something is added and the relationship that will always happen. What I always say, guys, always go back to your formula and see how you can actually use the formula to actually help you find your answer. This was a long paper for electricity, but what I can see is that it actually summed up everything, from internal resistance, EMF, as well as power in a circuit, as well as removing and adding and so forth. So questions like this are a very good practice question. So nonetheless, let's go to a quick ad break, and when we get back, I'm going to be doing more on electric circuits.
No one ever asks why we do the weird things we do. Like, why once is never enough? Or doing 2 trips is just one too many? Why do we, before we use these, or say 5 when we mean 20? Why do we have second thoughts? And think that lift buttons make them go faster? Why don't we walk there, cross our fingers, touch wood, and struggle to hide our true feelings? At Liberty, we want to know all the weird and wonderful things that make us human, because human beings, being human, are what we make financial solutions for. Liberty, in it with you.
Did you know that humans are born with 300 bones, but by adulthood they will only have 206? Human beings have 300 bones when they are born. Due to a process called ossification, the number drops to 206 by adulthood. Ossification is the process of cartilage changing to bone, which means that what may be 3 separate bones joined by cartilage in infants fuse into a single bone by adulthood.
Welcome back to another beautiful Tuesday afternoon that can only mean physical science with me, Utobile. I want to send a big shout out once again to Liberty. Thank you so much for sponsoring the show. Thank you for giving us this opportunity to help the class of 2021. Prelims are right around the corner. They start on the 23rd of August, which is actually next week, Monday. So all the best for that. And grade 12s, this is the best time to download the Tenfold education app. It is an app filled with tons and tons of past papers that can actually help you prepare for your final exam papers. Remember, with physics and mathematics and life sciences and all the other subjects, it's all about practice. If you want to join in the fun with what question paper we are doing today, please do send a hi to the WhatsApp number on the screen, and we shall then send you the question paper we are doing. Another platform where we are active and where we can actually help you guys is on YouTube. And on YouTube, please follow us on Mindset Learn. So without wasting any more time, we were looking at paper number 1, and we are doing electric circuits, one of my favorite topics. Very easy topic, really. A lot of theory, but needs a lot of practice. So in the previous question, we did a very long question, and I showed you how you can actually like some tips and tricks on how to answer the question, what the examiner is actually explaining, and where you actually get your mark allocation. I've got another question here, also on electric circuits, and the learner who has sent that question through, his name is Siabonga Senzo Map. So thank you so much for that question. And he says, Tops, please come to my rescue. How do you do these questions? I'm going to do it once again, one step at a time, and I'm going to show you the tricks and traits. Now remember, in order to learn electric circuits, it does start in grade 10. In grade 10, we learn some of the foundations, but majority of it comes from grade 11. If you can figure out that resistors in parallel have got the same potential difference and resistors in series have got the same current, then you can answer any question. And then, of course, your formula sheet, where you need to know what each thing in the formula sheet actually then represents. So without wasting time, let's see how we do this one. So now number 9.1 says, in the circuit diagram below, the battery has an unknown EMF. So this one was a bit because in the last one, they did actually give us the EMF, and it has an internal resistance of 0.8. Well, it's not much of a train smash, but let's see what we can do. So what am I seeing here? I can see that resistor number 4 and 6 are in parallel with each other. They have V1, which is in parallel with both of them. So now I can already see that the 4 ohm resistance has a current of 0.6, which means that if I can find the current for 6, the sum of these two resistors' current will be the total current in the circuit, which means that is then what will pass, or the current that will flow through A1. Another thing I'm picking up is that V1 is in parallel with these two, and we know that resistors in parallel have got the same potential difference, which means that V1 will have the same potential difference for 4 as well as for 6. I see that V2 is in parallel with a 5.8 ohm resistor. And then I've got A1 for the entire circuit. So I can think, what I can actually say is that most of my information is coming from this part here. I've got my resistance, I've got my current, and then I can find my V. Remember, I can use R is equal to V over 1, and then I can really find my V. And then once you can find that V, you can find anything else. So let's break it down. Let's do it step by step and see what the examiner was actually asking. Okay, the first one, 9.1.1 says, state Ohm's law in words. So let's state Ohm's law. And Ohm says the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. And there we are. So Ohm's law is the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature, and that's for 2 marks. And remember, guys, you can never fail because you're lazy to read. So we have another statement that says the reading on A2 is 0.6 amperes when the switch is closed. So I can see when the switch is closed, there is some current that's actually moving through. They want the reading in V1. So I just want to go back quickly. I see that A2, I'm given, it's already where I have the most information. They want the reading in V1. So this one shouldn't be too difficult. And it's only for 3 marks. So I can therefore say R is equal to V over I. I'm going to make V the subject of the formula because they are looking for V. So V will give me Ri. Remember, this one is over 1, and then I just cross multiplied. The resistor in question that they're talking about, it is a 4 ohm resistor, yes, and the current is 0.6. So my resistor is 4 ohms, my current is 0.6, and then they want the potential difference of that one. 4 times 0.6, and therefore I get 2.4. 2.4, and my SI unit for potential difference is therefore then a capital V. I just want to go back all the way to my diagram, and I'm going to say V1 is 2.4 volts. I also like using this system of working where if you are given a diagram, once you have any of the unknowns, go back to the diagram and plug it in. Now guys, don't sit for the whole exam period and draw the circuit. You can draw it, actually plug it in on your exam question paper. Use a highlight or something so that you can just remind yourself, okay, I do have this one, and so forth. You'll see the less unknowns that you have, the more sense it will actually start making. So for one, I do have my V1, which is 2.4. Let's see what the next question is going to be. Now they're asking us, we must find the current through the 6 ohm resistor. Now remember, the 6 ohm resistor is the one in parallel with the 4 ohm resistor. Let's go back to theory. With resistors in parallel, the potential difference will be the same, but the current will then split, which means that the 6 ohm resistor and the 4 ohm resistor will have the same potential difference, which will therefore be the 2.4 because they are in parallel. Resistors in parallel are current dividers. Resistors in series are potential different dividers. Always keep that in the back of your head. So let's calculate. So I'm looking for the current that will pass through the 6 ohm resistor. I'm going to do exactly the same thing. So I'm going to say R, I'm looking for the 6 ohm, is equal to V over I. My resistance is 6. The potential difference will also be 2.4 because resistors in parallel have the same potential difference. Over, I am looking for the current. This is now just mathematics. This is over 1, I'm going to cross multiply. 2.4 times 1 will give me 2.4. 6 times I will give me 6I. I need to find my I. I'm going to divide both sides by 6. This and this will cancel. So let's see what my current will be. So I'm going to have 2.4 divided by 6. So I get my current as 0.4 amperes. 0.4 amperes. I just want to show you another way in which you could have done it using ratios. Now remember, they are in parallel. So this means that the potential difference for the 4 ohm resistor is exactly the same as the potential difference for the 6 ohm resistor. Now, R is equal to V. Let me just do it the long way around. V over I, which means that R is equal to, which means that V is equal to Ri. I'm thinking of a lot of things in my head. Ri, because I just figured out something. So then, therefore, I can say Ri on this side, and I can also say Ri on this side. Therefore, I can then use ratios. For the 4 ohm resistor, it is 4 ohms. I did find the current as 0.6. In this side, I've got a 6 ohm resistor, and I'm looking for the current. If I multiply these two together, let's see if we can get that one. Let me just move that. So if I say 4 times 0.6, then I get 2.4. So I get 2.4 on that side, 2.4, and here I get 6i, which is exactly the same as this side. Divide both sides by 6. So you could have also used this ratio. It actually does work. 0.4 SI unit is then amperes. So that was also another method in which you could have done it. So now I've got the current for the 6 ohm. The only trick was for you to know that they share the potential difference. Just for argument's sake, guys, if you feel like you're not quite sure that this answer is correct here, please do continue to use it in the correct place in this step over here. Because in you are showing the examiner that, you know what, examiner, even though my V1 might not really be correct in the previous question, but I know exactly where to place it in the next one. So please do not make that mistake. Don't just skip the question to say, but my V1 is already wrong, so everything else is going to be wrong. Use the wrong V1 in the correct place in the next question, and then that we are then good to go. And then by 9.1.4, I must find the reading on V2. Now remember, V2 is the one that is in series, so there's a little bit of information that we need to plug in over here. By plug in, I mean that in the 6 ohm resistor, we did find that the current that will be passing through here is 0.4 amperes. Now I want you to think, if I've got 0.4 amperes coming here, joined by 0.6, which means that by the V2, I'm going to have the total current. I'm going to have I total that will be passing through here, which means I need to add this current as well as this current to give me I total that will be passing through the 5.8 ohm resistor so that I can find the unknown V2 resistor. Bit of a mouthful, but if this current again is incorrect, please do use the incorrect current in the right place. Just want to say it again. The current in this side, in this plot, remember, resistors in parallel are current dividers. Now I'm adding the divided current to give me I total since it'll all pass in 5.8. So let's find the reading on V2. So I'm going to say V2, I'm just going to skip a step here, will give me IR. So how did I find the current? Remember, it is the 0.6 ohms plus the 0.4 ohms, and we are talking about a 5.8 resistor. If I'm not lying, that should give us 1. Let me just double check, 0.6 plus 0.4. Yes, it does give it 1. 1 times the 5.8 remains in 5.8. So this will be 5.8 volts, and that's then the reading of V2. Just want to go back again. Let's plug that in. So V2, I just calculated it. We will be 5.8 volts. Let's read the next question. Number 9.1.5 says I must calculate the EMF of the battery. So there are various ways in which we can then calculate the EMF. Remember, when you're looking at your EMF questions, there's the E is equal to I, bracket R, and so forth. Or there's V is equal external plus internal potential difference. So in this case, I see that I'm not really given the internal resistance of the battery. Okay, I do have it. It's given to me as 8. So there's various ways in which I could use. Let's use the easiest method. Since they are in parallel, I think that we should use V external and V internal. But it depends on you. So now remember, if I'm looking at my external resistance, that will be V1 plus V2. V1 and V2 representing the potential difference for resistors in parallel as well as those in series. I do know that for the ones in parallel, we have found 2.4. For the one in series, it remained 5.8. Okay, let me not take a chance. Let me use a calculator for this one. 2.4 plus 5.8. And therefore, I get 8.2, and that is then my V external. This will be 8.2 volts. I'm not finished though. Then I'm going to say my V internal, and that is current times internal resistance. I know that the current in the system, we did add it in, I just want to go previously so you know where I'm getting the 1. Remember, the 2 split currents for the resistors in parallel was 0.6 and 0.4. Collectively, they gave us 1. So that is where I'm getting the current here, which is 1. My internal resistance was given to me as 0.8. If I multiply those two, it remains 0.8. Anything multiplied by 1 remains itself. And then therefore, that gives me a V. Therefore, I can then say my EMF is equal to my V external plus my V internal. There we are. My external is the 8.2 plus the 0.8. Okay, let's just calculate that one. So I must just add 8.2 plus 0.8 to that one, and therefore I get 9. So I've only tried it with this one. I didn't try it with any other method. But that's then how I would have found the EMF of that battery. It was only for 3 marks, quite a number of steps that we needed to use, but nonetheless, that's how we do it. Let me just extend my page again. So number 9.1.6, they say energy dissipated as heat inside the battery if current flows in the circuit for 15 seconds. So we must calculate the energy that would be as heat inside the battery if it flows for 15 seconds. Now, this one is then for 3 marks. So now, the one that I would use will be W is equal to VI delta T. Remember, this V is the one inside the battery. Inside the battery. So I just want to highlight that heat inside the battery. When they talk about inside, internal resistance, all right? Just want to go back to my diagram over here. We're given our internal resistance that we do have, which they gave us as 0.8, and then we do have the total resistance of the circuit. But in this case, they said inside the battery. They didn't talk about the previous question. Like if you remember correctly, the previous question, I think, talked about something in the power outside where it was 6 and so forth. That was outside the battery with the power of that circuit. In this case, they're talking about inside the battery. Anything inside the battery means internal resistance. So I want to be sure that you understand why I'm going to use the 0.8. So in this case, my V will then be 0.8, my current will be a 1, and then the time is 15 seconds. Luckily, it's already converted to seconds, so you're just going to plug that in exactly as it is. So I'm going to have 0.8, I don't have to put the 1, and I have to put the 15, and therefore I get 12. And that will then be 12 joules, and that is then for 3 marks. So that one was a bit easy. I didn't try it in any other method, but that is the way I would have done this one. I think the trickiest part of this question, once you could have found your V1, then you could have found anything else in the circuit. And then with the knowledge that the 2 currents need to be added as a total, since it will be the same current that will flow through. So that's how I would have done it, Siyabonga. Hopefully I've answered your question. Nonetheless, once again, guys, okay, they said I shouldn't go to an ad break. So let us go to another question. Let's see, which one are we going to do now? Let's do this one. This is question. Let me just see if we didn't do this one yet. Just help me. Did we do this one yet, Peggy? We didn't do this one yet. Okay, let's do this one then. So this one will start. So we have the battery in the circuit diagram below has an EMF of 12 volts. And an internal resistance of 0.5 ohms. Now, resistor R has an unknown resistor. I think questions like this always seem very complicated, but not so much. So I'm given the circuit, I can already see that the 2 ohm resistor and the R are in parallel with one another. Now, remember once again, resistors in parallel will have the same potential difference. Resistors in series will have the same current. Resistors in parallel are current dividers, and resistors in series are potential difference dividers. And as you can see how I keep doing, you always refer back to all that knowledge. So let's go back. So 8.1, what is the meaning of the following statement? The EMF of the battery is 12 volts. Now remember, for example, if you have a battery, if it has 12 volts, 9 volts, it actually tells us something on, the amount of energy that it can actually give in joules. In this case, if the EMF is then given to me as 12, let me just write it here. The battery supplies a 12, just write it like that. The battery supplies 12 joules per coulomb. And that was only for 2 marks, so that wasn't too bad. Then we have a continuing statement that says the reading on ammeter A2, so the reading on the ammeter is 2A, rather, when the switch is open. Let's see. So I know when the switch is open, the reading on the ammeter is 2A when the switch is open. Now remember what I said, if there's a switch that's open and there's a switch that's closed, it means completely different things. So let's start calculating here. Let's see what they've got for us here. Here they say we must calculate the reading of the voltmeter. So let's see where the voltmeter is. So I've got a voltmeter here. I don't know what R is, so I'm definitely using the total resistance formula is completely out. I've got my EMF, internal resistance, and then I've got my A since I am given that. So let's calculate that one. They did say it is open, so we have some V lost going on there. So I'm going to use the formula E is equal to I, bracket, and then I'm going to have capital R plus small r for internal resistance. I am told that my battery has an EMF of 12. That's what the statement was telling me, that the battery supplies 12 joules per coulomb. So that will then be 12. I am told that my I is 2. My R is something that is very unknown, so I'm going to keep that as R plus my internal resistance, which is then 0.5, and this is then just mathematics. I'm going to have 12 plus, I'm going to multiply in the bracket. So just keep that as an equal sign. I'm going to multiply that in the bracket. This will give me 2R plus, I'm going to have 0.5. 0.5, I'm going to multiply that by 2. So therefore, I have a 1. So that gives me 1. Now I have to still solve for R, mathematics. The 1 is going to go over the equation sign. Yes, at least Resistors is not going to be angry with me to say it's going to jump. It's going to go over the equation line, and then I'm going to have 2R. 12 minus 1 will give me 11 is equal to 2R. Now I still need to find the value of R by itself, so I'm going to divide both sides by 2. 2 and 2 will cancel, so R will give me, let's calculate that. I can take a guess, but let's just be sure. Yes, I was right, 5.5. So R will be 5.5 ohms. Now I just want to elaborate on something here. This R that we were looking for here is not the R of the unknown R. The R that we found here is the R for the entire circuit. I just want to go back to the formula. Remember, it's I is equal to I, total current, total external resistance plus internal resistance. So this R means the sum of the 2 ohm resistor and the unknown resistor. That's the R that we got of 5.5 ohms. So already if you had to find the unknown R, you can already see how you're going to find it, because you already have the total of the resistance in the circuit is 5.5. Now we already know that 2 plus something must give us the 5.5 for resistors in parallel. So don't be confused. That R is not the unknown R. It's the R for the total circuit. But I'm not finished. They did say they want the reading in the voltmeter. Just want to check where the voltmeter is one more time. This is the voltmeter over here. So I do have R. I can therefore find the voltmeter reading since I also have the current. So what am I going to do now? I'm just going to work over here. I'm therefore going to use the formula R is equal to V over I. Remember, R is the R that I just found. So they want the voltmeter reading, so that's going to be V is equal to RI. The R that I found was 5.5. It is the total resistance of the circuit. Therefore, I'm going to say my current. They did say when the switch S is open that we have a reading of 2 amperes. So that's where the current comes from. It is 2. If I multiply that by 2, I'm just the inverse of that. So that should then give me 11. And my SI unit for potential difference is therefore then a capital V. I didn't try it in any other way, so this is the one way that I'm going to show you. Now we need to find the resistance of R. So it's only for 2 marks, so it shouldn't be that hectic. I just want us to go back here. So we did find out that the voltmeter reading here is 11 volts. That's what we found out there. I still don't know what this one will be, but I do know that resistors in parallel have got the same potential difference. I also know that the current in this system, since we have here 5.5, will also then collectively be the 2 ohms. So let's find what the resistance will therefore be. I'm going to use the formula R is equal to V over I. I do know that resistors in parallel have the same potential difference. Therefore, that will then give me 11. The current will give me 2, and therefore I have 5.5 with that funny looking sign there being ohms. So now we have switch S is now closed. And this is for 4 marks. So I can already see what the examiner is trying to do here. Just one more time going back on what this means. So if ever the examiner is asking you about the switch is now closed, a resistor was added, a resistor was moved, you have to show them that you understand that there is a relationship with certain variables in an electric circuit when one is removed and one is added and so forth. It's also very nice to also use the terms directly proportional or inversely proportional and so forth. So you're showing the examiner that you also know the physics terminology. Remember, you do get marks for using those terminologies. So now we have switch is closed. I just want to go back to my switch over here. So this means, the switch is closed now. So this means that all of this is now operating. This means that the current will now split between the 2 and the R. Remember, if my switch is open, then the current cannot flow here, so technically it just flows through the one part of the circuit. So let's go back to this one. So for number 8.3, switch S is closed. How does this change affect the reading on the voltmeter? We must choose from increases, decreases, or remains the same, and then we need to explain our answer. Now think about it. My switch S was closed. It was technically only moving in this direction. Now, if you close the switch, I'm going to have current flowing in this direction and therefore current flowing in that direction. If you use the formula, if we look at the formula, R is equal to V over I. The minute we close or open a switch, we are actually affecting the current, which is I. I'm going to make I the subject of the formula here. I'm just going to do it the long way around, Ri, where I end up with I being V over R. So this means that my current, will be directly proportional to my potential difference, but inversely proportional to then my resistance. This means, just use a different color, it will decrease. It will therefore decrease because they are directly proportional. Remember, when we close the circuit, the total resistance decreases of the circuit. Let me just do it the long way around. When the circuit is closed, the resistance decreases. The resistance decreases. The current increases because now you have the current flowing in different directions. And then we have what we call lost volts. We have lost volts, which will increase. So technically what I did, I just used this one over here. When the current increases, my resistance will decrease because they are inversely proportional to one another. And that's what the examiner was saying. You do get a mark for saying decrease and as well as explaining what is then happening. So that is how I would have answered this question. Thank you so much for joining me on this beautiful Tuesday afternoon, and I will see you next week.